Hello, everybody. This is for the problem question 3 in week 8, section algebra of the course for the course Maths 1251 at University of New South Wales. Okay, in this question we have a complex numbers, and complex numbers can be viewed as a vector space, real vector space. And the basis will be 1 and I, because 1 and I can span whole of, if you take your scalars from the real numbers, 1 and I, all the linear combinations of 1 and I, 1 plus I, and the lambda plus mu I, will give you the complex numbers. That's the definition of the complex numbers. So complex numbers is a R vector space, is a real vector space. We specify domains and codomains with respect to these maps. These are the maps, and we will decide also whether they are linear or not. We will decide their domain, their codomain, and whether they are linear or not. Okay, for first one is the every complex number goes to the real numbers. So the domain I'm going to show as a domain T, and codomain is codomain T. This is the notation we usually use. Some people may use different notations depending on the person, but usually the dom and codem is a good enough notation. Okay, a notation. So domain means that domain of a transformation, domain of a map, means that whatever that map is defined on. So you have some elements, you have some vectors from the first set that you're starting with. This is your input set, okay? Domains are your input sets. Your input sets, and then you define a map taking the inputs to go to the output. So outputs are the codomains and inputs are the domains. Let's put it that way. So for these, every complex numbers goes to the real numbers, means that every x plus iy goes to the x. So everything in the first space, which is the input space, is the whole complex numbers, because this is defined for all complex numbers. So the domain is the complex number. So that's that one. That's easy. What is the codomain? When we define this, everything in this map goes to only the real numbers. So the whole complex plane goes only the real plane. That's the x-axis. That exists still in there because t goes from z to the z, right? This is all T maps from the Z to Z, from the complex numbers to the complex numbers. But when we define this with this way, it will be always only the real numbers on the other side. Output only restricted to the real numbers. So the codomain will be only the real numbers. So T is an identity map on the real part of the complex number. So as R itself is a vector space over itself with dimension 1, T is linear. So this part is basically, it's good enough to say it for a person who knows what is the vector space, what's the dimension. But if we want to prove, if we want to show that T is a linear map or not, we need to prove it. What was the linearity condition? You can separate and you can have a look as a two axioms rather than one axiom. I'm doing here only one axiom type. So I'm taking scalar number from any two scalar number from the real numbers, any two numbers from the complex numbers, and linear combination of these two complex number linear, and apply to the T transformation should give me linear transformation. Linear is lambda times Tz plus mu times Tw is a linear combination of lambda mu of Tz Tw. So the linearity is preserved by this map. So how can we prove it? It is easy. Directly, we can write it. The Z will be lambda Z1 plus lambda Z2. Mu W will be mu W1 plus I mu W2. So collecting to the real parts and imaginary part of this whole complex number before we apply the T, because T is taking the complex number and only output will be the image, a real part of this complex number. So this is a complex number as a whole, but we need to tidy up a little bit so that we will know the real part and imaginary part. It must be clear for us before we apply the transformation. Okay, this is the real part of this complex number, and this is the imaginary part. According to the definition of this map, this T transformation gets any complex number as an input, as an output, gives us only the real part. So this is the real part of this complex number. Now, this is lambda and Z1, and Z1 is also is TZ, right? If you take the transformation here, the real part of this is Z1. So this is basically TZ. Z1 is TZ. And then the W1, when we apply the T on W, we will get W1. So that's TW. So in one line, you can prove that T is a linear map in that fashion. You can also separate these two properties. You can have a look Z plus W, and in another property is like Z time lambda times Z. Addition in one property and another one as a scalar multiplication as another, or you can join together and use this as a to prove it. Okay, I'm not going to do the second part because second part is exactly the first part. Only you have the imaginary. So instead of the tx plus iy goes to x, it will be tx plus iy will go to the y. So there's no I here, right? When we have imagination of imaginary part of z will be just y, not iy, even though that's the I part of it. So you can similarly prove with the same steps, everything will be similar to that one by taking the what we've done in the A section. There's no point for me to do that. And for this map is TZ is goes to the absolute modules of the Z. An absolute value function on the complex numbers we call modules, and the modules are defined as if you have a complex number x plus iy is equal to square root of x squared plus y squared. We know this definition. We've done it before. Now we would like to see that whether it is linear or not. First, let's define what is the domain and codomain. Domains are all our inputs. That's all complex numbers. Because this map is defined for all complex numbers. Well, how about the codomain? Codomain, what are the outputs? Well, this is always a positive number, right? Because we are taking the square and then the square root. It is always a positive number. So the modules of a complex number is always positive, bigger than 0 for all complex numbers. So the codomain of the transformation T is a positive real numbers. So we can write the positive real numbers as a notation like R plus or R bigger than or equal to 0, or you can choose a superscript, or you can choose a subscript, you can choose plus, you can choose bigger than or equal to 0, but all of them means that we have x are the real numbers such that the x bigger than or equal to 0. So this is our codomain. Is this linear? It is not linear. It is easy to, if we want to show that it is not linear, it is good enough to show a counterexample. And the simplest counterexample for this one is t minus z. If we have a minus z, a minus of this will be minus y minus x minus y. When we take the square root, squares of it, and then the square root, it will be the same thing as z. So this is what I'm trying to say is that t minus z, which is the minus z modules, is equal to the z module, which is tz, but that is not minus tz. But we know that one of the property of being linear should be the scalar multiplication rule. If we have t lambda z, we must have lambda tz. This must equal. But in this case, they are not equal. It means that t is not linear. Scalar multiplication rule for this map is not satisfied, so t is not linear. It was kind of an obvious because this is not a linear expression. You can have such clues in the question. Okay. In this one, we would like to we have complex number z, and the tz is defined as a map, is the argument of z. Here is the argument means that is the angle which defines the complex number. We know that the complex numbers can be written as x plus iy, or can be written as r e to the I theta, and the angle gives us the argument. Argument 0 is not defined, so 0, we know what's an argument means, so I don't want to go into too much, but we can express every z in a different way. It goes to the argument means that this angle is defined. So, but in this definition, the output, so input is the every complex numbers. So domain is the complex number, but z is equal to 0. We don't have argument of z. So that means that it is not defined. So the domain for t, we should subtract the origin in the complex plane. And similarly, what is the codomain? Codomain will be not just the angle between minus pi, or we can minus pi, and pi is because this is the principal argument. This is the first round. It's minus pi from the round from here to here, or round from here to here. Right? This is what it is. This one or this one. So codomain is -1 between minus pi and plus pi. That's what it goes. So the codomains are codomains are not vector spaces. So there is no discussion about the t being linear in this condition, because we don't have a vector spaces. The first condition for your map, for your transformation to be linear, we are talking about the maps between vector spaces such that the linearity preserved by that map. If you don't have a vector space to start with as an input and an output, if you don't have inputs or output or both are not the vector spaces, you cannot talk about the t being a linear or not. It is an illogical question after all. So that's the situation for this part. The last part, tz goes to z conjugate. So this is defined for all complex numbers. And the codomain will be the all complex numbers. And if we think about the addition, then we have z plus w complex conjugation. But we can separate this complex conjugation as the sum of the complex numbers. Then we do have tz plus tw. So this is the first rule. And for scalar multiplication, scalar times to the complex number complex conjugation, we can separate them. That is a complex conjugation of lambda and complex conjugation of z, and product of them. From here to here, we have this property. From here to here, lambda is a real number because we are thinking the complex numbers as a real vector spaces. So lambda is a real number. In a real number, there's no complex conjugation. Complex conjugation of a real number, it's itself. So this one is itself. And this is Z bar, Z complex conjugation. Z complex conjugation is by the definition is TZ already. So addition, vector addition, and scalar multiplications are both preserved by this BEP, and so T is linear. I could have done with the one-line proof as I've done in the section A, sorry, above in the section A. I could have done this way, but I wanted to have another option to show you another option for the proof. So, you can do it in one line, actually, so no problem. Yes, that's all for this question. Hopefully, this information is helpful for you all. Thank you very much for listening.